limestone, fizz, but not sandstone, clay or granite. When calcite is held in a flame with tweezers, the colour of the flame changes to brick red. With rock salt it changes to yellow, and with copper to blue-green. If possible, keep your specimens in a cabinet after they have been labelled and wrapped in paper. Now this book is from 1966, so it's quite old. The nature of the earth. The earth is full of wonder. As you look into the sky at night, thousands of stars sparkle like diamonds. All thinking people have asked themselves, where did the world come from? One thing is certain, the earth is part of a large plan called the solar system. The sun is at the centre, and round it travel the planets, our Earth, Mars, Jupiter, Venus, and many others, circling like a giant gathering wheel. One of the possible explanations of the origin of the solar system is that a large passing star came close to the sun and pulled out a large part of it like a giant tooth. This streamed away in a burning gas, and within this flaming gas, spots cooled down, changing into the planets. Over 4,500 million years ago, our Earth cooled down into a hot liquid ball, on the outside of which a skin slowly formed. This skin became the crust, with giant mountains and hollows. The rains came and ran down into the hollows to make the oceans, whilst the higher parts formed the continents. Inside the earth. Another question everyone asks is, what would I find if I dug a hole to the centre of the earth? Some of the deepest coal mines go down 3,000 feet, passing through layer after layer of rocks to reach the coal seams. The oil men drilled holes more than 20,000 feet down, but these are only pinpricks in the earth, which is nearly 4,000 miles to the centre. Beneath the farmers' fields are layers of rocks called strata, many of which contain fossils of animals which lived long ago. These help us to say how old the rocks are. Below the first 10 miles, the strata begins to disappear and solid granite is found. The continents of the earth are like big rafts of granite floating on a plastic layer called basalt. Sometimes this basalt escapes to the earth's surface and spills out of volcanoes. Further inwards are heavier spheres of metals, the centre one being the heaviest substance, believed to consist of iron and nickel, and extremely hot, as much as 4,000 degrees centigrade. These heavy metals are also found in meteorites which fly around in outer space. So you can see the nickel-iron core in the centre, and then you've got the inner mantle and the outer mantle. Earthquakes. Nature has damage than the hydrogen bomb. 30,000 people were killed, and it blew the island off the earth. Wow. Vesuvius in Italy is a famous volcano. In AD 79, the Romans living in the city of Pompeii suffered a disastrous eruption. The exploding mountain buried the city with ash and dust, killing 2,000 people. Archaeologists have now uncovered parts of the city again. The people of a tiny island, Tristan da Cunha, in the South Atlantic Ocean had a similar experience. Their mountain suddenly erupted and everyone had to escape in boats from the hot lava flowing down over the island. Volcanoes occur where the Earth's crust is weakest and eruptions start deep down. Here the rocks are very hot and under great pressure. Sometimes the pressure builds up until it blows a hole through to the surface, and up this chimney flows the lava. Rocks from the sea. The rivers of the world are constantly taking tiny particles off the land and spreading this sediment over the seafloor, where it builds up layer upon layer, forming sedimentary rocks such as sandstone and clay. Big rivers like the Thames and Rhine carry millions of tons of mud into the sea. The Mississippi River takes 24,000 tons of chemicals and over 1 million tons of mud into the Gulf of Mexico each day. We make many things from these sedimentary rocks. Bricks are made from clay rocks, as are plates, cups, saucers, roof tiles and drain pipes. We are able to reach this clay because the sea has sometimes changed its position and these rocks have become dry land. Limestone and chalk are also sedimentary rocks, being formed over millions of years by the shells of dead sea creatures which sank to the seabed. Fossil creatures such as ammonites, coil shells found in limestone prove that the strata were once beneath the ocean. Limestone was used to build the Houses of Parliament, and in the Pennines the rock is burned to make cement and to build as lime. A rock garden in the sea. Just as millions of years ago the limestone rocks were formed from the shells of tiny living creatures, so today is the coral barrier reef of Australia being formed by life in the ocean. This reef is made of millions of tiny animals called polyps, growing in the warm, shallow waters of coral seas. The reef is like a beautiful underwater garden with sea anemones, tiny bush-like branching corals, mushroom-like fungi and others, all brightly coloured and spreading fine tentacles into the sea, extracting food for their life and lime for their hard shells. When they divers enjoy exploring the underground passages and caverns. The Mendip Hills are made of the same kind of rock. At Cheddar, the caverns are very large, and here can be found giant stalactites and stalagmites. These have been formed over millions of years by the constant dripping of water from the roofs of the caves. Each drop of water leaves a tiny crystal of lime on the roof, and gradually a long stone icicle, a stalactite, is formed. Each drop falling on the floor leaves another crystal there, and so builds upwards to make a stalagmite. Crystals formed in this way sometimes fill up cracks in the rocks, when they are known as veins or lodes. Other minerals are produced by great heat and pressures deep in the earth. Diamonds form this way. Some minerals are brought up from within the earth by very hot liquids. Lead is formed in this way when the hot liquid cools and results in a mineral vein. Lead. Among the wonders of the ancient world were the hanging gardens of Babylon, built on pillars 300 feet high. These terrace gardens had flower beds lined with lead to hold water. This was one of the earliest uses for lead. The Romans also were expert builders, and many of their camps had baths fitted with lead pipes. At Bath, these pipes are still in use after 2,000 years. When the Romans lived in Britain, they searched the hills for galena, the commonest lead ore, which they found as grey cubes in the limestone rocks. The Romans called it plumbum, and so a plumber was someone who fixed water pipes. Galena is now melted in furnaces and treated so that the hot lead runs into moulds where it sets. Because it never rusts, it was often used on the roofs of churches, but now it is too expensive. Nearly 1/3 of all lead used today goes into batteries, as every motor car must have one. Telephone cables under the sea are lead covered. Paint contains lead, and so do the sinkers, boots used by divers. Iron ore and steel. Lodestone is nature's magnetic iron ore, magnetite, and the first compass used by sailors was a floating needle of lodestone. Iron ore is a very important mineral, as many things like bicycles, cars, trains, gas stoves and tools start as ore in the earth. Pyrites, siderite and hematite are the commonest iron stones, the last being the most important. The making of steel begins when glass factories, window glass, jam jars, and many glass ornaments are made. Crystal quartz is very useful in radio stations and radar instruments. Pure radio quartz controls the radio waves, but it is very scarce. Scientific lenses and dishes, which must resist acids, are also made from quartz. Graphite. Writing is easy with a piece of graphite because it is a soft stone which makes black marks on paper, as well as soiling the fingers. The ancient Greeks who used this black stone called it graphite, meaning writing. Graphite has often been mistaken for lead because it has the same colour, and this is why we speak of lead pencils, which are not really lead at all. The thin lead in a pencil is made by mixing graphite powder with clay and heating it in a furnace to over 1,500 degrees centigrade. Soft leads have more graphite than hard ones. Nearly 1/10 of all graphite mined is used in pencils, but its chief use is for making special cups and basins in which to melt brass and other metals. Dynamo brushes are also made of graphite. Sometimes oil cannot be used on machines in cloth factories, as it might run and mark the material, so powdered graphite is used instead. Atomic power stations use a lot of graphite because an atomic reactor is made by placing rods of uranium in huge blocks of graphite. Sulphur. When Guy Fawkes tried to blow up the Houses of Parliament, he used the only explosive then known, gunpowder. Sulphur is part of the recipe for making gunpowder, and although modern explosives do not use gunpowder, it forms part of the fireworks we buy for November the 5th. Sulphur is sometimes called brimstone or burnstone, as it is one of the few minerals which melts easily and catches fire. It burns with a terrible smell and choking fumes, just as a volcano does when it erupts. Burning volcanoes, geysers, and hot springs give out sulphur fumes, and in New Zealand and Iceland, the caves are often lined with lovely yellow sulphur crystals. Sulphuric acid is the most important product made from sulphur. Large quantities of this acid are used in the manufacture of fertilizers for agriculture, in the making of paint, and in the production of paper, and rayon from wood pulp. Natural rubber is too soft for motor tyres, but when sulphur is mixed with it, the rubber becomes very hard and tough. This is called vulcanized rubber. Fluorspar and blue john. Fluorspar is not a very common mineral in the British Isles. It is mined in only two counties, Derbyshire and Durham. The word fleur means to flow, and this describes the main use of fluorspar in purifying steel, silver and gold. For every ton of steel in the furnace, 10 pounds of fluorspar are added to make the waste products flow off as a scum on the melted steel. In this way, the purified metal is left behind to set in ingots. The second main use for this mineral is in the pottery industry. It is one of the substances used to make the enamel on the baths and kitchen sinks in our homes. Natural crystals are found in the limestone rocks of Derbyshire and Durham, and are shaped in cubes is as clear as glass, but when you look through it, you discover it is a magic mineral. Everything appears to be doubled, and words are blurred because they appear to be written twice, closely side by side. Turning the crystal, the letters slowly join together and then separate again. This is called double refraction. The best crystals come from Iceland and are known as Iceland spar. This mineral is used inside the special microscopes which geologists use to look into rocks. Experts testing diamonds, emeralds and other gemstones use special instruments containing Iceland spar lenses to find out if the gems are genuine. Impure calcite is a very common mineral found in all limestone hills, like the Pennines and the Cotswolds. As we have seen on an earlier page, the stalactites and stalagmites, which are found in the caverns of these hills, are made of millions of tiny crystals of calcite, formed from the lime in the water which trickles through the rocks. Rainwater slowly dissolves limestone and passes on into rivers, making the water hard. This causes kettles to fur up with hard stony lumps, and the water pipes in our homes to become blocked with a crust of lime. Rock salt. It is impossible to sink in the Dead Sea because it contains so much salt. The River Jordan brings in the salt, and the hot sun evaporates the water from the sea, leaving the salt behind. The salt layers in the rocks in Cheshire were formed millions of years ago, when seas and lakes dried up. Now miners work 400 feet underground in big caverns, taking out rock salt, which is made pure in the factory on the surface. Salt is a vital part of our daily lives. We all eat about 12 pounds each year. It is put into the cooking, and food is sometimes stored in salt. Animals need salt, so the farmer buys salt lick for his cows. Chemicals are made from salt, soda being one of the most important, as it is used in glassworks and in soap and paper making. Chlorine from salt purifies water and makes acid as well as cleansing powders. Salt melts ice on the doorsteps of our homes, and nowadays large quantities are mixed with sand to help roadmen to clear snow from the roads. China clay. Near St Austell in Cornwall, large white mounds can be clearly seen on the hillsides. These are China clay workings, and this soft white clay is a very special mineral. It is called kaolin, a Chinese name for some hills in that country from which pottery clay has been obtained for many years. 200 years ago, we bought clay from China, but now we find enough in Cornwall and Devon. Large patches of kaolin are found in the granite rocks where strong gases have attacked the crystals and caused the rocks to crumble. Here, the miners wash out the soft clay with powerful jets of water. Large quantities of China clay are sent to the factories at Stoke-on-Trent to be made into cups, saucers, plates and all kinds of pottery. Another use for this pure clay is in the manufacture of certain kinds of paper. These papers have a smooth, glossy surface necessary for some methods of printing. Kaolin is also used in the manufacture of rubber, paint, linoleum, soap, face powders, stomach powders and poultices. Asbestos. Asbestos looks more like a plant than a mineral from the earth. It is nature's rock wool because it is made of soft, silky fibres which can be easily so that great thicknesses of dead plants piled up on top of one another. The bottom of the swamps continually sank, and sometimes water completely covered the forests. When this happened, rivers brought in tons of mud and covered all the swamp plants with layers of rock. In this way, the forests were squashed into coal seams. 200 feet of rotting plants made a coal seam 10 feet thick. Above these seams and rocks, swamp forests grew again, later to be submerged in turn. This went on for millions of years, gradually forming the coal seams of today. Mining and using our coal. A modern coal mine is like the Underground Railway in London, but very much deeper. Bradford Colliery near Manchester goes down over 3,000 feet. Every day, many miners go down the main shaft, each one carrying a lamp on his helmet. Special electric or diesel trains take the men several miles to their work at the coal face. In the older pits, the miners have a hard task breaking the coal and loading the wagons. The modern mines have powerful machines which rip out the coal and load it onto conveyor belts to start its journey to the surface. Powerful railway engines pulling 100 tons of coal make many journeys to the main shaft. Here it is like a railway station, complete with signals, fluorescent lighting and automatic telephones. Coal has many uses other than for fires. Gasworks use coal to make gas, and at the same time produce chemicals for dyes, paints, soap and many other things. Iron and steel works use many tons of coke every day, and electricity is made at some power stations by burning coal dust. Every year our miners produce 200 million tons of coal. This would fill a coal train 50,000 miles long and stretching twice round the world. Silver. Silver has been used since 4000 BC to make fine ornaments and jewellery. Many were discovered in the ancient tombs of the kings of Persia and Mesopotamia. The Spaniards were looking for silver in Peru and Mexico when they explored South America, and there they discovered nuggets weighing nearly a ton. The Spanish galleons were real treasure ships carrying the precious metal back to the King of Spain. Coins have been made from silver for many centuries, but as it is very soft, it has to be mixed, alloyed with copper and nickel to make it hard. Special chemicals which are very sensitive to light are made from silver. This is the secret of taking photographs with a camera or films for the cinema or television. The reel in the camera contains these very sensitive chemicals. We all look into the mirror every day, yet it is the silvered back of the glass which really reflects. Some silver is mined out of the earth with gold, but most of this metal is found mixed with lead and copper ores in Bolivia, Mexico and Peru. Gold. In the days of Pharaoh, 3,000 years ago, the Egyptians were using gold to make beautiful cups, bowls and necklaces. These are still as perfect as when they were first made. Gold is the king of metals because it never loses its bright colour or decays away. This is why it has been used for centuries as money. The Mint in London is the place where coins have been long made from bars of solid gold. Gold leaf is made by beating it into thin sheets, and this is possible because it is a very soft metal. Usually it is hardened by being mixed with copper or silver. The purity of gold is measured in carats. 24 carat is pure gold, which is too soft for use. 14 carat is the usual strength for pen nibs. Wedding rings are Countless tiny animals, once living in the oceans, sank into the muds on the seafloor and changed into specks of oil. Other deposits followed and formed into rocks. A long time afterwards, gigantic forces within the earth raised these rocks from the seabed to form new land, and often rock arches were created. Into the crests of the arches oil was squeezed and trapped. Boring a hole into the rocks takes a long time and costs over £300,000. The crude oil from the borehole is a mixture of many kinds. One part may be suitable for jet aeroplanes, another for cars, some for diesel engines, whilst the bitumen, pitch, is used on the roads. The refinery splits oil into the different qualities, and some help to make rubber, linoleum, waxed containers, plastics, perfumes, medicine, disinfectants, etc. Diamonds and pearls. The earth sometimes yields rare and priceless gems. King of all gemstones is the diamond. This is the hardest mineral on earth, and impure diamonds are very useful for cutting steel, making grinding or polishing wheels, rock drills and diamond-tipped needles for record players. The crown jewels in the Tower of London contain the world's finest diamonds. The royal sceptre has the largest of all, the first star of Africa, flashing its emblem of justice and kingship. The imperial state crown, used to coronations, has the second star of Africa. These came from the largest stone ever found in South Africa, the Cullinan diamond. A diamond is a simple substance because it is pure carbon, but it has been made into a crystal by great heat and pressure inside the earth and brought to the surface by ancient volcanoes. Pearls are gems from the sea, formed in some oyster shells when sand irritates the animal inside the shell. The animal covers the sand grain with mother of pearl, and the pearl grows bigger each year. Divers find pearl oysters in the Red Sea and Indian Ocean. Radioactive minerals. Ours is the atomic age. It began when Professor and Madame Curie discovered radium in 1898. Professor Curie found that radium gave out invisible rays which could pass through many things, and he called this power radioactivity. These rays have special powers useful for combating some illnesses. Some of the Earth's minerals show this radioactive power very strongly. Pitch blends is the best known because it contains radium and uranium. In 1939, scientists succeeded in as well as this video today, I'm also planning a video where you will actually see me in the video. Don't be too afraid. It's only going to be very short, but I just wanted to personally thank everybody as myself, rather than you just seeing my hands. And so keep an eye out for that later on. But first things first, let's get back to this lovely library book. So I'll just pop that there. So this is one of the library books that I got a couple of weeks ago. In fact, it's probably due back soon, so we better get on with it. It is called The Land, Extreme Earth. Splits open, volcanoes erupt, tornadoes destroy, rivers overflow. And I thought we could have a look at this, and I've had a quick flick through. It looks quite interesting. It's quite a big book, quite heavy. So I need to make sure that I get this within the camera frame. Okay, just maneuvered it slightly. So, Extreme Earth. And there's an introduction by Simon Winchester, and we have chapters on earth, air, fire and water. So I think we'll skip the introduction and go straight to some of the pictures. Some of the pictures are marvellous, really nice. So this section is about Earth. So this picture is Mount Everest. It says Earth's highest point. The location is central Himalaya on the border of Tibet and Nepal. It has a total height of 8,850 metres. And I'll read this section at the bottom. Known in Tibet as Jomolungma, or Goddess Mother of the Snows, and in Nepal as Sagamatha, Mother of the Universe, Mount Everest has seen more than 150 climbers die on her icy slopes. Yet still they come, alone or without oxygen, like Austria's Reinhold Messner. Others ski down, as Yuko Miura of Japan did in 1970. And this picture is Earth's highest landmass, the Plateau of Tibet, location southwest China. Height above sea level is 4,000 to 5,500 metres. In his classic 7 Years in Tibet, Heinrich Harrer wrote, "It took all our energy to collect yak dung and find water, and even talking was a waste of strength. was the youngest member of our team and played a relatively modest role, so this climb was my chance to shine. Joe was on his first visit to the Himalayas, but his reputation as Britain's finest rock climber preceded him. Everest had been climbed several times within 300 metres of its summit before ultimate success, but we were trying the largely virgin southwest face of Kangch, where no one had ever surpassed 6,000 metres. Our objective was to reach the Great Shelf, a prominent ice terrace at 7,300 metres. Just in case things proved easier than expected, we took oxygen and sufficient equipment to attack on the summit. This climb had one unusual feature. The eastern half of the mountain lies in the Indian state of Sikkim, where the people regard Kangchenjunga as a god. It was sacrilege to desecrate its summit, so we promised not to pass the point from which we could see an easy route to the top. We would not tread on the summit itself. Over 4 weeks we devised a route that bypassed a treacherous lower icefall and kept to the central cliffs of a steep upper icefall, where we were relatively safe from avalanches. After setting up camps and escorting Sherpa teams carrying supplies, we were ready to launch the assault in pairs on successive days. First Joe and me, then Norman Hardy and Tony Strather. That night, Joe and I made a lemon drink from crystals and tea with lots of sugar to prevent dehydration. Supper was asparagus soup from a packet, a small tin of lamb's tongues with dehydrated mashed potatoes, and a nightcap of drinking chocolate. Then we crawled into our sleeping bags, wearing every scrap of clothing we had, even our boots. We didn't want them getting frozen stiff like Hillary's on Everest. We kept on our climbing rope and anchored it to a nearby rock spike in case the tent slid off the ledge. We shared a cylinder of sleeping oxygen at 1 litre per minute each, but I didn't sleep well. I was too excited. The others had done their utmost to get us so high, and we didn't want to let them down. I prayed for good weather. By 8:15 a.m. we were climbing the icy gangway leading to the West Ridge. There were tricky pinnacles on the ridge, so we planned to turn off the gangway and tackle the face directly. Because the ground was a mixture of ice, snow and rock, we took off our crampons and treated it more like a rock climb. We aimed for a little subsidiary snow ridge that led back up to the West Ridge, then climbed to a sensational rocky eyrie on which we were poised mid-air, thousands of feet above the shelf and glacier below. We reached the ridge at 2 p.m. with only a couple of hours of oxygen left. We should turn back by 3 p.m, Joe, I said, or we may have to spend the night out. We've got to reach the top before then, he held back. Keeping just below the ridge to avoid the wind, we came up beneath a nose of rock that reared up, sheer and smooth. The wall was broken by several vertical cracks, about 6 metres tall, with a slight overhang at the top. Joe was keen to try one, with his oxygen turned to the full 6 litres per minute, and safeguarding his lead with a couple of running belays, he forced his way up and I followed. Before us, some 6 metres away and 1.5 metres above the ground on which we stood, was the very top, formed by a gently sloping cone of snow. We had come as far as we were allowed. Many people have asked whether I was tempted to tread those last few feet. The answer is no. I was very tired and glad for any excuse to stop, but what a view! successfully repeated our climb the next day. Being more practiced at climbing ice than rock, they kept their crampons on. They didn't like the look of Joe's vertical crack near the top and instead carried on around the corner, where they found an easy snow ridge running up to the summit. But they also stopped short out of respect for the god of Kangchenjunga. No one climbed the mountain again for 22 years. is 55 million years old. And here we have Earth's longest sand dunes. The Simpson Desert in Central Australia, total length 200 kilometres. This is a bigger picture of it. And here we have a diagram of the comparison between the different sizes of deserts. So the largest one, number 1, is the Sahara, in this creamy colour, North Africa. Number 2, this one here, is the Australian desert in Australia. Number 3 is the Arabian desert here, and the location is Southwest Asia. And number 4 is the Gobi Desert, and the location is Central Asia. And number 5 is the Kalahari Desert in South Africa. And here, that's a great picture, look at this. This is Earth's largest gypsum dune, the White Sands National Monument, location New Mexico, USA. And here we have Earth's largest sand island, is Fraser Island in Queensland, Australia. Total size is about 171 kilometres square. is Earth's longest cave system. This is the Mammoth Cave in Kentucky, central USA. And the total size is at least 566 kilometers in area. And here we have Earth's longest, deepest, narrowest slot canyon. And this is Buckskin Gulch in Utah, Arizona border, USA. It's 21.6 kilometers long, 244 meters deep in places. Earth's largest crater is the Sudbury crater in Ontario, southeastern Canada, and it's 140 kilometers wide. And this page says that Earth's largest volcanic crater is Toba in northern Sumatra, Indonesia, at 1,160 kilometers square. And this picture, let me read the little text at the bottom. A local legend tells of a man living in Danau, Toba, who caught a fish in his trap, which miraculously turned into a beautiful princess. She agreed to marry him as long as he promised to never say anything of her origins. Years later, scolding their child for eating his midday meal, he lost his temper and exclaimed, "You damned daughter of a fish," and thus unleashed an earthquake. And this diagram shows Earth's largest volcanic calderas. This red one here is Danau Toba in Sumatra, Indonesia. Number 2 is Yellowstone caldera in Wyoming, USA. Number 3 is Taupo, North Island, New Zealand. And number 4 is Long Valley, California, USA. I'm just going to take some more coffee. And here we have Earth's largest island, Greenland, location North America and the Arctic Circle. It's 2,166,086 kilometers square. And here we have Earth's fastest growing island, which is Iceland on the North Atlantic Ocean. The place I'd love to visit actually, one day. Wow, look at this is the California's 1,200 kilometre long San Andreas Fault. Marks the boundary between two plates and causes about 10,000 mostly small earthquakes each year. This fault system runs almost the entire length of California and is in some spots as much as 16 kilometres deep. The land moves across the San Andreas Fault at a rate of 56 millimetres a year. And this picture is Earth's largest unbroken, unflooded caldera, and it is at Ngorongoro Caldera, location Tanzania, Africa, and it is 264 kilometres square. And this is the Serengeti National Park, which contains the Ngorongoro Conservation Area. And I think these are, let me see, are these wildebeests? Yeah, wildebeests. And on this picture we have Earth's largest wildlife refuge, the Serengeti Plain. Location Tanzania and Kenya, East Africa. And here in this photograph is Earth's largest earthquake, which is Valdivia, May the 22nd, 1960. That's when it happened. The location was off the southern coast of Chile, and the magnitude of 9.5. Wow. Gosh. Just let me have some coffee first. And this picture represents Earth's deadliest earthquakes. And the deadliest one seems to have happened on, or at least when this book was published, the 28th of July 1976 at Tianjin, China, magnitude 7.8. And this picture is Earth's greatest continental collision, Hindu Kush in Central Asia. Gosh, look at this, a little bit of fertile land right in the middle of all these Rocky Mountains. And here is Earth's largest landslide, Mount St. Helens, Cascade Range, southwestern Washington, USA. So this picture says Mount St. Helens shortly before its earth-shattering blast in 1980. This mudflow was triggered by a minor eruption. And this picture represents Earth's extreme avalanche zones. The Swiss and Italian Alps, the western United States and Canada, Rocky Mountains, Cascades. South America is the Andes, Asia, Himalaya, New Zealand, Southern Alps, and the coordinates vary, of course. Great picture. Wow, look at this. This is Earth's largest This is Earth's most otherworldly badlands. This is Bisty Badlands in New Mexico, USA. That's a fabulous photograph. Wow, look at this. This is Earth's biggest mushroom rock, the Red Sea Desert in Israel. And it says here, you may never happen upon the caterpillar from Alice's Adventures in Wonderland. Oh, we've just read this. Perched upon a mushroom rock and puffing away on his hooker. But these strange ancient sandstone formations do inspire curious comparisons. Animals, birds, faces, buildings, people. One observer even reports seeing a kneeling camel. This is the National Park in Western Australia, and these are limestone stubs of ancient fossilised trees. Gosh, look at these. There's obviously once a forest here. Right, a bit more coffee. And this picture is Earth's oldest fossil. This is the Warrawoona group in Western Australia. And this amazing picture is Earth's strangest sandstone formations. It is Cappadocia in Turkey. Oh, look at these. They look like little houses. Let me read this to you. Oh, people lived here. Wow. People lived at Zelve Valley until quite recently, hollowing chambers into the soft rock. There are even two sacred enclaves, the Fish and Grape churches. Elsewhere in this amazing region of central Anatolia, Turkey, at Asikli, Oyuk, relics including tools and religious objects dating back to Neolithic times have been found, along with the skeleton of a woman in her early to mid-20s, showing evidence of the world's first known case of tree banning. Tree banning, I don't know what that is. I feel as though I should know what that is, but I can't remember. I've heard the word before. Somebody will tell me anyway. It's important to share knowledge, I think. Anyway, this picture here, this represents Earth's most calcified places. And there are three here. There is Mono Lake, California, USA. The Mammoth Hot Springs, Yellowstone National Park, Wyoming, USA. And Pamukkale, Hierapolis in Turkey. And this is Hierapolis in Turkey. Gosh. Wow, look at this. This is Mono Lake, I think. Yes. and driven by two elite Danish soldiers. I caught a special glimpse of how the world and its inhabitants adapt to the most extreme of environments. It was minus 40 degrees C on the eastern coast of Greenland at the Mestavik Army Base in the middle of nowhere, accessible only by satellite phone and the Danish mail service. It was 10 p.m. and a cold breeze was cutting across at 48 kilometers per hour, 30 miles per hour. A light dusting of snow was kicked up and swirled as the dogs, part wolf and part Inuit husky, drove off their hind legs, howling and barking with the thrill of an expedition. The expedition in question was a short one, in fact a short hop and parcel dispatch. The parcel was me, and the repository was a snow hole on one side of a hill that was to be my home for the night. The night was glorious with moonlight, throwing a pink hue on a glossy white landscape. Earlier in the evening, the northern lights had danced sea green across the sky for us, taking on the perfect shape of a seahorse. I watched, mesmerised, sinking and slipping on the snow until I lay flat on my back for 10 minutes, dazzled by nature's greatest show. The wispy green apparition faded peacefully away. Still drunk on the experience and a couple of glasses of red wine with Commander Norrit and his Danish SAS unit later, I prepared for my night in the snow hole, an experiment constructed by the producer to make my life as uncomfortable as possible. One of these days they'll kill me off. The next morning, as we left the compound, at quite a belt, I noticed one of the dogs in the middle of the pack veer left off the track. His body turned, but the momentum of the pack kept him in line. The dogs with their thick fur might be oblivious to the cold, but dog number 7 was not oblivious to the Arctic hare sitting tall about 50 metres, 45 yards off the moonlit track. Soon the others caught the scent and veered off in the direction of the snow-white hare. In the pink glow, its outline was discernible only by its dark eyes. As 13 howling wolf dogs raged towards it, the hare moved not a jot. It knew that, more than any creature there that night, it was adapted perfectly to the environment, so instead it just stood tall and surveyed its patch, showing no sign of fear. The dogs jangled in their chains, a triumph of breeding and adaptation, struggling against the army handlers who crackled them into line. The men, wrapped in down, were trained to live unsupported with the dogs in the most extreme conditions on the planet for 3 months at a time. The army's elite force learned to tolerate just their surrounding, and each man had his own bag of tricks and socks to deal with what is frankly an inhuman climate. And then there was me, a freezing, terrified Londoner, trained for nothing and adapted to no climate except one where central heating and a good pub are nearby. But what a world the weather offers us, and how remarkable it is that we can adapt and mould and mutate to survive in the most arduous of climactic and environmental conditions. I've travelled the globe tasting and touching the worst and the best of the world's weather, from the Sahara to the tropics, from the blast of the vast net wind to the silence of the doldrums, and from the heat of Arizona to the wet of the Belizean jungle. And the truth is that no animal on the planet can survive its variety and extremes of weather and climates better than man. In the Arctic, the hare is entitled to disagree, but that is its kingdom. Across the globe, the awesome and inexplicable truth is that the human body is a remarkable machine that has habituated itself to a wild and turbulent world. I use man in the general sense. Me, I'm still all at sea without my central heating and my pub. So this chapter is called Weather World. Says, weather is in us and all around us, a huge interconnected force of chaos, creation and destruction. It is also the thin veil that shrouds our planet and defines the limits within which we can stay alive, the temperatures below and above which our bodies will cease to function, the forces of wind and flood that we can withstand, or the electrical charge that can instantly destroy us. Seeds of weather. Now this picture is, it says, the dry, freezing cold surface of Mars with its empty pink sky, photographed by the Pathfinder lander in 1997. And here, the thin layers of the Earth's visible atmosphere, the veil of weather on which we all depend. Okay, so let's read. Let's read here. Wind, wet, hot and cold. We live in the Goldilocks zone, neither too hot nor too cold, too wet nor too dry, too windy nor too calm. By the sheer chance of planetary mechanics, Earth is the perfect home. Our neighbours in the solar system, Venus and Mars, are in just the wrong position for the weather to have worked out perfectly. Venus is too close to the Sun, and its atmosphere is a searing, boiling greenhouse of immense pressure that would simultaneously fry you, crush you, and dissolve you in acid were you to venture out onto its surface, while Mars is too far away and is a frozen world with almost no atmosphere at all. But on Earth, the forces of geology, biology and chemistry flow hand in hand, behaving as a single living entity, and the weather we experience is effectively the breathing of that living planet. For our life is intricately linked to the weather. We depend on its remarkable system for the air we breathe, the water we drink, and the growth of the food we eat. The weather defines the limits within which we can stay alive, the temperatures below and above which our bodies will cease to function, the forces of wind and flood that we can withstand, or the electrical charge that can instantly destroy us. Throughout human history, the weather has been a dominant factor in our lives. Drought and rain have always been the controllers of famine and plenty. Storms and calm have limited our global exploration and ocean trade, while individual lives have been saved by a shower of rain or swept away by a gale. Civilizations have fallen and wars have been won and lost on the turn of a few days' weather. It dictates the cultural attitude of whole nations. It has been at the degrees F Fahrenheit. But the energy generated there goes through a series of epic permutations before it reaches the surface of the Earth. It begins as gamma rays produced by the nuclear reaction, but these quickly degrade to X-rays. These radiate from the core until the temperature is cooled enough to allow volumes of gas to carry them rapidly in giant cycles of convection to the surface. There the temperature is much more comfortable, a mere 6,300 degrees C, that's 11,350 degrees F. This journey of energy from the core to the sun's surface can take 1,000,000 years or more. As they near their journey's end, the X-rays lose energy, so that what emerges is first ultraviolet and then finally the bright, visible light that we see at the surface. There, in the turmoil that exists, the constant leaping of electrons to and from different states of energy, as they orbit the nuclei of their atoms, releases photons or light energy. These photons radiate out towards the planets, travelling at the astounding speed of 300,000 kilometres, 186,000 miles a second. In just over 8 minutes, the photons strike the Earth, where, as each one is absorbed by the ocean, by a cloud droplet, by a rock, a plant, an animal, or you and me, it adds to the energy that warms the surface of the planet and adds to the force that is at the heart of our weather. This picture A succession of intrepid flyers went up to have a look. Many carried rudimentary instruments with them to measure the atmosphere through which they flew. Crude versions of the barometer and thermometer had been invented some 150 years previously, and gradually a map of the layer of air above our heads was built up. Falling temperatures and lower pressures were experienced the further up the explorers ventured, and many reported strange ill effects like bleeding from the nose or difficulty in breathing. Some fared far worse. In 1862, James Glaisher, a founder of the British Meteorological Society, was dispatched to investigate precisely what occurred at height, along with an experienced balloonist, Henry Coxwell. The balloon was a gas-filled canopy with sandbags for ballast, and carried a variety of instruments to measure air temperature, pressure and humidity, magnetic fields and the spectrum of the sun. The two men even had a crate of pigeons to test the effect of altitude on animals other than themselves. The morning of the flight dawned with a threatening sky, but the men wanted to go ahead, so the balloon was launched right into the clutches of a rising rainstorm, and they were sucked up into a thundercloud. They suffered the terror of rising through the thunder and lightning of the storm, only to emerge miraculously out of the side of it. They continued to climb, taking measurements as they went. At 5,000 metres, 16,500 feet, and -8 degrees C, 18 degrees Fahrenheit, a pigeon was tossed over the side and fluttered chaotically towards the earth. At 7,000 metres, 23,000 feet, another luckless pigeon plummeted far from view before regaining some kind of aeronautical control. At 8,000 metres, 26,000 feet, the last two pigeons refused to get out of their cage. Then disaster. Concentrating on their experiments, Glaisher and Coxwell failed to notice that the release cord for the gas valve was tangled up out of reach. They had risen to 9,000 metres, 30,000 feet, and with no way of letting the gas out of the balloon, they seemed doomed to go on rising, becoming ever colder and ever more short of oxygen. By now, breathing and movement were painful, but Coxwell managed to climb into the rigging to try to reach the cord, then found that his fingers literally froze to the metal structure that held the gondola, and that he was trapped, unable to move up or down. Glaisher, meanwhile, was losing his sight and his mental faculties as he struggled for oxygen and failed to understand when Coxwell yelled for help. But Coxwell managed to keep control and caught the swinging valve cord in his teeth. Twice he tugged at it with his head, once breaking a tooth and once tearing through the flesh of his cheek, and then for the third time he bit onto it, clenching with all his might, and jumped. Tearing his frostbitten fingers from the rigging, he crashed with good fortune back into the gondola. The gas valve wrenched open above them, and their gradual descent and recovery began. They had reached 11,000 metres, 36,000 feet, close to the limit of human survival, and they had charted their way to the top of the weather. There were more balloonists, more courage, more disasters, until the limits of balloon flight were reached in the 1950s, touching altitudes of 31 kilometres, 102,000 feet, where it is possible to see thin layers of the atmosphere that wrap like the skin of an onion just 7 kilometres, 4 miles, over the poles, and above most of the populated areas of the northern hemisphere, only a 10-kilometre, 6-mile thickness of weather lies above us. On a planetary scale, this thin veil is an almost non-existent place in which we survive, a thin blue gas which sustains our life. Fortunately, it is enough. At any one time, we are wrapped in about 5,600 trillion tons of air. Each one of us breathes about 10 million times a year, using only about 5 tons in that time. So there is plenty of it to go around. How that air moves and behaves, along with the myriad particles of dust and molecules of water that it carries with it, in other words, how it creates weather, is governed by the forces of heating and cooling described earlier, but also by another property of our Earth. Okay, so I'm going to leave it there. Well, there's quite a lot of dust in this book. I will leave it there and we will continue this very interesting book on weather in another video. So, this has been Kate at the Library Whispers saying I shall see you very, very soon. Bye bye for now. Bye bye. Hello everybody, it's Kate at the Library of Whispers, and today we're going to rejoin this lovely book before I have to take it back to the library. It's called Extreme Earth, and this section is about so let's take a look. Wow, what is this? This is Earth's largest ozone hole. explorers were their ancestors playing ball with a walrus skull, and that the lights could be attracted to Earth by whistling or repelled by barking like a dog. Auroras also hold spiritual significance to most northern peoples and are considered gifts from the dead to light up the long polar nights. Earth's most electrifying place, Kampala, Uganda, Central Africa. Look at this. First came the accidental discovery by Luigi Galvani in 1786 that an electric shock could cause a dead frog's legs to twitch. Scientists today think that lightning actually switched on evolution in the primal soup. By 2001, Pascal Simonet and his team at the University of Lyon, France, used bolts of electricity to make bacteria swap DNA with one another. Wow. Polar. Oh, look at that little hut amongst these trees, I suppose, covered in snow. Earth's greatest snowfalls. Greatest depth is Tamarack, California, USA, 1911. And the greatest single snowstorm was Mount Shasta Ski Bowl, California, USA, 1959. Earth's rainiest and wettest place. Well, can I just say, I'd like to claim that record for the place that I live in, which is the north of England, because we are going to have an awful lot of rain later this evening and overnight. However, the book says that it is more Sinram in Meghalaya, northeast India. Yeah, we shall see. We might break that record tonight. What a great picture. Earth's windiest place. I think we could maybe also claim that at the moment. Commonwealth Bay, southeast Antarctica. I do love these pictures. Whoa, look at that. That's a tent. Does it say? This tent, torn down by the scything winds of Antarctica and half buried in snow, illustrates the irresistible force of violent wind as it howls across the frozen continent. What little shelter it might have provided has gone. A reminder of the extreme hardships endured by generations of polar explorers, and one that brings home the significance of Captain Oates' words as he left the Scott expedition's tent for the last time. I am just going outside, and maybe someday across southern Illinois and into southwestern Indiana. Biggest super tornado outbreak, 1974. Coordinates across 13 US states. Wow, look at this. Wow, that's incredible. You can see the power of nature in that picture. And this one is Earth's greatest tree loss by windstorm, December 26th to the 27th, 1999, across France. I remember that. Earth's most destructive hurricanes. Biggest Hurricane Mitch, November 24th to 27th, 1998. Location, Central America. Area of greatest rainfall, La Quiba, Honduras. Most expensive, Hurricane Andrew, 1992. Location, Bahamas, Florida and Louisiana. I'm not quite sure when this book was published, but I think a lot of these records have probably been superseded by now. That's an amazing picture. Earth's worst tropical cyclones, longest lasting, Hurricane Typhoon John, August and September 1994. Location, Pacific Ocean. Deadliest, Bangladesh cyclone, November 1970. Storm. Whoa. Fork lightning. So we're now on to fire, which is the third chapter. Wow. So, Earth's largest flood, basalts. Siberian traps, Russia, 2 million kilometers squared. The Deccan traps, India, 500,000 kilometers squared. And Lucky basalt, Iceland, 565 kilometers squared. Wow, look at that. Wow, this is Mount Ararat. Is singled out in the Bible as the landing place for Noah's Ark at the close of the Great Flood, a patch of divinely ordained dry land after 40 days and nights of deluge. Geologically, Mount Ararat is a harsher place. This imposing basalt boulder, so reminiscent of curved ship timbers, was blasted from the ancient volcano in the Aras mountains of eastern Turkey Guatemala, 1902, 4,500 deaths, and it caused disease. Number 9. Galunggung, Indonesia, 1882, 4,011 deaths, caused ash flows. And the last one, Vesuvius, Italy, 1631, 4,000 deaths, caused ash flows. And that's an unusual thing there. What is that? This is Earth's largest lava tree grove in Kilauea, island of Hawaii, Big Island, Hawaii, USA. It almost looks like two people holding each other rather than a tree. Earth's most buried volcanic massif, Tongariro, New Zealand's North Island. And this is Earth's most volcanic zone, the Ring of Fire encircling the Pacific Ocean, a range of coordinates. This is Mount St. Helens. This is the island of Java. Look at this. And this is the final chapter, water. This might just be my favourite chapter. I love water, expanses of water. I mean, I like the drink too, but rivers and seas. But this is when water is at its most destructive, of course. Earth's most powerful tsunamis. Tallest, Latoya Bay, Alaska, USA, 1958. Fastest, Hilo, Hawaii, USA, 1946. Deadliest, Krakatoa, Indonesia, 1883. Ocean. Wow. This is Earth's largest submarine sinkhole, the Blue Hole, Lighthouse Reef, Belize, total size 300 metres across, roughly 137 metres deep. And here we have Earth's longest reef and largest coral domain, the Great Barrier Reef, Australia's northeast coast, 2,012 kilometres long, or 350,000 kilometres square total area. Wow. No, I love that photograph. Amazing. total size about 696 million kilometers squared of water. The Earth's smallest ocean, the Arctic Ocean at the North Pole, 14 million kilometers squared. Earth's largest sea, the South China Sea, location between the Southeast Asian mainland and Taiwan, the Philippines and Malaysia, total size 2,590,600 kilometers squared. And this is a diagram representing Earth's 3 oceans or 4 oceans. Don't know what number 4 is. So 1 is the Pacific Ocean. Number 2 is the Atlantic. And number 3 is the Indian. But I don't know where the Arctic is. No. Don't know. Anyway, Earth's longest river is the Nile in Central and North Africa, 6,695 kilometers. And here we have Earth's most deadly flood, Huanghe Yellow River, 1931, China. Wow, look at this. Fjord, Nordvest Fjord, Skorresbysund, Eastern Greenland, 314 kilometers. This is Earth's deepest crevasse, Antarctic Glacier, East Antarctica. Whoa, love that picture. That looks like the inside of a whale. This is Earth's largest ice cave, and it is in Eis-Riesenfeld, Austria. Probably not pronounced that very correctly. Wow, they look like pyramids. This is Earth's largest salt flat in Salar de Uyuni, central Bolivia, 17,480 kilometers squared. And this is Earth's lowest surface point, the Dead Sea, Israel-Jordan border, 403 meters below sea level. Earth's deepest and oldest freshwater lake, Lake Baikal, southeast Siberian, Russia, 1,742 meters deep, or 31,494 kilometers squared of fresh water. And I think we may be near the end, not quite. Okay. And here we have Earth's largest saltwater lake, the Caspian Sea, Central Asia, 371,000 kilometers squared. Love that picture. This is Earth's highest lake. This is Lecangapur Lake, northern Chile, 5,930 meters above sea level. And here we have Lake Superior, Earth's largest freshwater lake in North America, 82,414 kilometers squared. And here is a diagram of Earth's largest lakes. So number 1 is the Caspian Sea in Northwest Asia. Number 2 is Lake Superior, North America. Number 3, Lake Huron, North America. Sorry, I beg your pardon. Number 3 is Lake Victoria, Africa. Then number 4, Lake Huron, North America. And 5 is Lake Michigan in North America. Earth's hottest place under the ocean, the hydrothermal vents location, the Mid-Atlantic Ridge. This is Earth's biggest body of water, is Lake Natron, border between Kenya and Tanzania, 56 kilometers This is the white line in the Pacific, is the result of a massive collision of fish, foam and tiny algae called diatoms. And that's the end. Well, I hope you enjoyed looking at those pictures. Thank you so much for joining me. This is Kate at the Library of Whispers saying, I shall see you very soon. Bye bye for now. Bye bye. Hello everybody. This is Kate at the Library of Whispers. And today we're going to take a look at a lovely library book. This one is called Atlas of Oceans, Exploring This Hidden World by John Fondon. I love the cover. Let's have a look inside. Now, I picked this book because it looked as though it had some really nice photographs inside. Look at the penguins. Now the contents are introduction, 8 oceans in peril, ocean world, rocks and water, the moving ocean, ocean life zones, coastal waters, temperate waters, tropical waters, polar waters, open waters, the ocean deeps, and then another section, the world's oceans and seas, the Atlantic, the Pacific, the Indian Ocean, the Southern Ocean, the Arctic Ocean, the seas of Europe, the seas of Eurasia, and the South China Sea. And then there's some more sections: Ocean Future, the Sea Epic, Endangered Marine Species, Further Resources, Glossary, Index, and Acknowledgements. Oh, look at that photograph. Wow. Now it says this is waves of water meet waves of sand in this aerial view of the Pacific coast of southern Peru. The beach has formed crescent-shaped dunes, which are caused by strong winds along, always oriented in the same direction. Fabulous. So this is the introduction, Oceans in Peril. Ocean Watch. Now let's move on a little bit, and let's start with ocean geology, ocean world, rocks and waters. Now this other fabulous photograph here. The world's shorelines are the scene of an epic battle between the oceans and the land that has continued for many, more than 4 billion years, and has seen the rocks of the shore shaped and reshaped countless times. geological scale, a human life is but the tiniest blink of an eye, but as the ocean floor moves through the ages, they form new marine habitats again and again, reshape the seabed, throw up undersea mountains, shift rocks and mud in coastal waters, and change countless other factors that affect the balance of life in the sea. the species without doing grave harm to the whole ocean ecosystem. Ocean creatures are not so nearly restricted to particular habitats as land animals tend to be. Salmon, for instance, spend some of their lives at the head of freshwater rivers and some thousands of kilometres away in the deep ocean, two dramatically contrasting places. Nevertheless, the ocean can be divided into biomes or life zones, depending essentially on the distance from the shore and the depth from the surface, which controls how much light they receive, among other things. Exploring the deep. The world's sensors. This is an interesting looking creature. Let's see. When sensor scientists discovered this octopod, its large fins led to it being dubbed the Dumbo, after the cartoon character. The biggest species of Dumbo octopod is quite naturally named the Jumbo Dumbo. Coastal waters. The world's 1.6 million kilometres, 1 million miles of coastline, where the land meets the sea, is a narrow zone rarely more than a few hundred feet wide. Yet it presents an extraordinary range of habitats for life, from shining white coral sand beaches, lapped only by the gentle waves, to rugged cliffs pounded all through the year. Ever-changing shoreline. Russell's book out of the way. Pop him up there. And I'm going to show you the coffee first. And this is it. It's called Little's Chocolate Caramel Flavour Infused Instant Coffee. And I found this in a small shop. I kind of liked the little jar and the screw top and the pattern and also the flavour, obviously. And what does it say on the back? It says 100% Arabica coffee, gently infused with the taste of chocolate and creamy caramel. No added sugar, 4 calories per cup, and it's 50 grams. And the little blurb on the back says, "Liven up your cup. Let's face it, some instant coffee can be a bit dreary and boring. Well, not on our watch. Our flavour-infused coffees are made using smooth 100% Arabica beans, gently infused with high-quality flavours from ingredients we love. We don't add any sugar, and each serving only contains 4 calories. We are here to liven up your cup and show you that instant coffee doesn't have to be boring." By somebody called Will and Caroline. So I'll open this and show you. I've actually had a cup of this already. So I've taken off the gold seal that was here. Let me use my spoon. It does just look like instant coffee, but the smell is absolutely gorgeous. I wish we had smelly vision. It's so chocolatey, such a chocolatey taste. Anyway, we'll have one of these coffees another day. And the next thing is I'm going to have my herbal infusion. And you will notice that this time I brought a little bowl with me to put the tea bag in. I've not been very organised in the past. Oh, there's a bit of coffee. I actually nearly ate that thinking it was chocolate, but of course it dropped. It would be quite bitter. There it is. Let's pop in there. It's called Cinnamon Herbal Infusion. And it's actually cinnamon and peppermint black tea. So I'm going to open this box, and if it's too noisy, we might have to skip this bit, as usual. Yes, it was too noisy. So I think there are 20 sachets in here, and these are all individually wrapped. Governor's Estate Cinnamon Herbal Infusion. Let's move the box out the way. Bring my cup over. Open up the packet. I have to say I do like these little individually wrapped tea bags. I think they're quite cute. Oh, I can smell it. Very nice, minty and cinnamony. nice colour, like a light gold with a hint of green. I don't know how much of the cinnamon flavour I will taste, because mint can be quite overpowering, I think. Let's use my spoon. Now I presume you can leave this in for as long as you like, really, depending on the strength of the tea that you require. Those of you who now know me and have watched my many tea videos will have seen that I don't really like a strong tea, so I think it's probably time to take it out and put it in this little bowl. Move that out the way. That looks nice. It smells divine. Let's have a taste. Oh, that's very nice. That's actually delicious. The mint doesn't overpower the cinnamon at all, but on the other hand, the cinnamon doesn't overpower the mint, so you've got that nice, very subtle mix of flavours, which actually is very refreshing. Yeah, I would say that's quite a summery kind of drink, although you would think that maybe cinnamon would be quite wintry, autumny, but that's really refreshing. So I'll clear up these things and we will take a look at the fossils book. So, see you in a minute. So here we are. I've moved the camera down a little bit so we can see the book a little bit better, and move my tea to this side. So let's have a look at this book on fossils. Oh wow, look at this. So the contents are, there's an introduction, then invertebrates, all those things, vertebrates, plants. And this is the author's introduction, so let's have a little read of this, because this might be interesting. Fossil collecting is a fascinating hobby which has grown considerably in popularity over the last few decades. Its appeal is understandable. It combines the excitement of discovery with the practical skills of collecting and preparing specimens, and the academic challenge of identifying fossil finds. There are few other branches of science in which a beginner can make a serious contribution to the knowledge of our planet's remarkable prehistory. In 1910, Sir Robert Falcon Scott embarked on his historic but tragic expedition to the South Pole. On his return from the pole, Scott and 4 companions met their death in freak weather conditions. Out of this tragedy came an important scientific discovery among the personal belongings of the dead explorers. A fossilised seed fern, Glossopteris, was found. The existence of this seed fern proved conclusively that the frozen wastes of Antarctica were once part of a fertile continent, and it is known that Scott had recognised the scientific importance of his own find. From coins to bones. Originally, the word fossil derived from the groups that lived long before historic times. Years of speculation. Fossils have intrigued people for generations. Greek philosophers regarded them as rather strange natural phenomena, which formed in the earth in a similar way to a stalactite or crystal. Martin Luther, 1483 to 1546, believed that fossil finds on mountain tops were evidence of the biblical flood. In his notebooks, Leonardo da Vinci, 1452 to 1519, suggested that fossils were the petrified remains of once living organisms. His views, heretical for his era, were withheld until his notebooks were published in the 19th century. The true nature of fossils became slowly apparent in the 17th and 18th centuries. This was aided by the publication of books figuring collections of fossils and by a wider understanding of natural history. One key observation was that different types of rocks contain different fossils. This fact was of considerable help in the production of the first geological maps and led to the modern sciences of paleontology, the scientific study of fossils, and stratigraphy, the study of rock strata. Today, paleontology is concerned only with the remains of animals and plants that lived more than 10,000 years ago. Tea time. Classification. Fossils are usually referred to by their two-part scientific name, although a few have popular or informal names as well. For instance, the oyster Gryphia is often called a devil's toenail, and brachiopods are known as lamp shells. These names have their uses but lack the precision needed in science. More importantly, they are not internationally accepted and can be confusing. The usual form is to give the scientific name, usually written in italics, followed by the name of the author, the person who first described the species. The first part is the genus, the second part is the species. If the author's name is in brackets, it means that the species has, at a later date, been moved to a different genus, when correctly used as scientific. Name refers only to a single type of organism and can be understood by scientists all over the world. The basic unit of classification is the species. There are many and varied definitions, but essentially all members of a species look similar and are able to interbreed. One or more species may be grouped into a genus, linked by features they share. This, along with the family, a group of genera, and the order, a group of families, makes up the pedigree of family tree of an organism. All the stages above species are artificial, a man-made classification, and they tend to change depending on current opinion. This can be frustrating to beginner and specialist. So let's see, what is a fossil? Let's look at some of the pictures. This one here, reptile footprint. While difficult to identify to a particular species, fossil footprints can provide valuable information about the organism's behaviour, such as speed, weight, and mode of life. Fossil dung. Trace fossils or true fossils. This dropping here is probably from an extinct shark. It is usually difficult to relate process known as mineralization. This chemical change often enables the fossil to become more resistant than the surrounding sediment. Now this is modes of preservation. Now I recognise this one. This looks a bit like the colour of my tea. Trapped in amber, just like Jurassic Park. Amber, the fossilised resin of a plant or tree, sometimes preserves not only the external but also the internal structure of an organism. Insects, spiders above, frogs and lizards may be preserved in this way. This one is silicification. This is a form of petrification. Silicified wood, or silicified could be silicification. Silicified wood can be found in both terrestrial and freshwater deposits, usually sands and silts. Weathering volcanic ash usually supplies silica, which is gradually incorporated into partially decayed wood. Generally, the cell structure of silicified wood is quite poorly preserved. However, the presence of iron and other minerals can produce some really spectacular colouring. And this is phosphatization. Bones and teeth above, which normally dissolve on the seabed or leach from the sediment, are more likely to be preserved if large quantities of phosphates are present. Phosphatic deposits are a source of well-preserved fossils and are often mined commercially. And this rather gruesome looking thing is mummification. The dry, sterile atmosphere of a cave has preserved this moa foot with some soft tissue intact. Usually, bones are only preserved in a fragile state. Mummification is only a pause in disintegration and is not true fossilization. Freezing. This Siberian mammoth's hair right was preserved in permafrost until recently. Once thought it will decay unless action is taken, but the hair is relatively durable. And this one is tar and sand. A mixture of tar and sand has embalmed this beetle. This could be stable for thousands, but not millions of years. This is a limestone tomb. The completeness of this fragile crinoid, entombed in limestone left, suggests that the calcareous nodule encasing it formed soon after death. And this one is pyritization. The shell and chambers of this ammonite rite were replaced by iron pyrite. This is often unstable in moist air, so it must be stored in very dry conditions. I think I'm probably already mispronouncing things. Never mind, have more tea instead. And this is a geological time chart. this one was found. It says Concorvi left. An eyeless deep water genus was found in a hard Cambrian mudstone. And these are the things, the tools that you would use. Different kinds of chisels and hammers and things. Sieves, spade. Preparing your collection. From hobby to science. Now this is fossil identification kit. Okay, let's give this a go. The fossil record is so vast that to give adequate coverage in a book of this size is impossible. Nevertheless, typical examples of most of the more common groups of fossils have been illustrated here. In this way, even if a particular genus is not illustrated, a similar organism will be shown. Over the next 8 pages, visual examples of each major group of fossils are given, along with a concise description and the pages of the book where the group is covered in detail. When attempting an identification, it is vital to relate the range of any fossil to the rock in which your particular specimen is found. For instance, you do not find trilobites in the Cretaceous nor mammals in the Devonian. A look at the geological time chart on pages 14 to 15, which we skipped over, will help you with this. The key is divided into 3 sections: invertebrates, vertebrates and plants. So these are the invertebrates, and this one is called Foraminifera. Worms. That was pretty easy to pronounce. Burrows, tracks or calcareous tubes, usually spiral, cemented to objects. Can be confused with pteridinid tubes. Scaphalopods or corals. Range Cambrian recent. Sponges and bryozoans. Trace fossils and problematica. Graptolites. Corals. And these are arthropods, trilobites, chelicerates, crustacea, insects, brachiopods, mollusks, bivalves, chitons and scaphopods, gastropods, nautiloids, ammonoids, belemnites and squamates. just take the last little bit of tea and I'm all done. So I'm going to end there and hope you enjoyed taking a little look in this fossils book with me. Thank you so much for popping by. This has been Kate at the Library of Whispers, and I shall see you very soon. Bye bye for now. Bye bye. Hello everybody. It's coffee time. Just gonna have a sip. This is Kate at the Library of Whispers, and today we're going to continue to read this book on the oceans, the world's last wilderness revealed. A gorgeous, darling Kindersley book. Now, I think I want to start this video by looking at ocean life, and I thought I would mark a page where we would start with my pointer here, and I thought we would look at animal life because some of these pictures look really interesting. Look at this fish. So let's start with reading from here. Animal life first appeared in the ocean over 1 billion years ago. It has since diversified into a vast array of different organisms. The range of scale among marine animals is immense. The smallest invertebrates are over 500,000 times smaller than the largest whales. Despite the huge disparity, animals all share two key features. First, they are heterotrophs, meaning they obtain energy from food. Second, they are multicellular, which distinguishes them from single-celled life forms. So this picture shows an example of an invertebrate. The yellow tube sponge from the Sea of Belize is a typical sessile invertebrate. Instead of moving to find food, it filters out particles of food by pumping water through its pores. And here we have changing shape. Most invertebrates change shape as they develop. Feather stars start as drifting larvae, which eventually attach themselves to corals or rock before changing into swimming adults. Marine animal diversity. Animals are classified into 30 or more major groups, phyla, of which include at least some marine animals. 29 of these phyla are composed of animals without backbones, invertebrates, each phylum representing a completely different body plan. Only one phylum, the chordates, contains animals with backbones, vertebrates. In salt water, vertebrates include fish, reptiles, birds and mammals, animals that are often described as the dominant forms of ocean life. However, in terms of abundance and diversity, invertebrates have a stronger claim to this title. Invertebrates exist in all ocean habitats and outnumber marine vertebrates by 1,000,000 to 1. They include an array of fixed sessile animals such as corals and sponges. They also form most of the zooplankton, a drifting community of animals and animal-like protists. Support and buoyancy. On land, slice up soft-bodied animals, such as jellyfish, enabling them to grow large. They use internal pressure to keep their shape, the same principle that works in balloons. Animals with hard body parts, such as fish and mollusks, are often denser than water and would naturally sink. To combat this, many have a buoyancy device. Bony fish have an adjustable gas-filled swim bladder, while squid have an internal float made of chalky material containing many gas-filled spaces. Some surface dwellers, such as the violet sea snail, have gas-filled floats which prevent them sinking. So I think this is the violet sea snail. Yeah. So it produces a kind of mucus which hardens, forming a raft. That's clever. Groups and individuals. Among marine animals, there is a social spectrum from species that live on their own to those that form permanent groups. The whale shark here is a typical solitary species, spending its entire life on its own, apart from from when it breeds. It can do this because its huge size means it has few natural predators. Smaller fish often form shoals, which reduce each fish's chance of being singled out for attack. Many invertebrates, from corals to tunicates, live in permanent groups known as colonies. In most coral colonies, the individual animals or polyps are anatomically identical and function as independent units, even though they are joined. Other animal colonies, such as the Portuguese man-of-war, are made of individuals with distinct forms. Each form carries out a different task, like parts of a single animal. Fascinating. I do love this picture. I was just going to say, let's have some soup. No, it's not soup, it's coffee. The reason I have soup on my brain, as an aside, is because I've made some soup and I'll be having it for lunch. Anyway, back to the oceans. So this picture says Sea Symphony. Let me see. A wrasse, that's what this is called, feeds among coral in the Red Sea. Coral reefs contain the greatest diversity of animal life in the oceans and are one of the few habitats that are actually created by animals. Now these pages are about sponges. Okay, let's move the coffee shadow over to that side. This abundant and diverse group of often colourful invertebrates lives permanently attached to the seafloor. Naturalists once thought they were plants, but they are now known to be very simple animals with no close relatives. Sponges live by drawing water into their bodies through tiny holes called pores. aquatic sponges grow large enough to fit a person inside. Wow. Their hard surface is deeply ridged, but their rim is thin and delicate. The barrel sponge belongs to the Demospongi, the largest class of sponges, containing about 95% of sponge species. The skeleton of sponges in this class is made from both scattered spicules of silica and organic collagen called spongin. An almost identical barrel sponge, Cestospongia muta, occurs in the Caribbean. And across here we have the breadcrumb sponge. This is Alicondria panicia. This one. The appearance of this soft encrusting sponge varies from thin sheets to thick crusts and large lumps. On wave-exposed shores it usually grows under ledges as a thin green crust. Its osculi, opening at the tops of small mounds. Its green colour is produced by photosynthetic pigments in symbiotic algae in the sponge tissue. In deeper shaded waters, the sponge is usually a creamy yellow. In waters with strong currents, this sponge may cover large rocky areas and kelp stems. This is a weird one, look at this. This is called a lemon sponge. You can tell why. This is Leucetta jagosensis. The lemon sponge is a beautiful bright yellow colour and is easy to spot underwater. It grows in the form of sacs which may have an irregular lobe shape. Each sac has a large opening, the osculum, through which used water flows out of the sponge. Through the osculum, entrances to the water intake channels that run throughout the sponge can be seen. The lemon sponge belongs to a small class of sponges in which the mineral skeleton is composed entirely of calcium carbonate spicules, most of which have 3 or 4 rays. The densely packed spicules give the sponge a solid texture. Like all sponges, this sponge is hermaphroditic. It incubates its eggs inside and releases them as live larvae. Through the osculum, each larva is a hollow ball of cells with flagella for swimming. There's an awful lot of Latin in this book. Oh wow, look at these. What is this? This is called now how do you pronounce this? Now, is that a silent C? Is that Nidarians or Cnidarians? I don't know. It's an ancient group of aquatic animals which emerged in pre-Cambrian times about 600 million years ago. It includes reef-building corals, anemones, jellyfish and hydroids, most of which are marine. Does anybody know whether that's a silent C in that word? So this here is building reefs. Coral reefs are built by colonies of coral polyps that secrete a hard exoskeleton of calcium carbonate. As the tiny polyps divide and grow, the reef expands. vicious stinger. As well as having 8 stinging tentacles, it is covered in tiny red spots that are bundles of stinging cells. The sting is painful but not dangerous. The morph stinger glows by producing luminous mucus from surface cells when it is knocked or disturbed by waves. Hanging down from the underside of the mushroom-shaped bell are 4 long, frilly mouth lobes, which are sometimes called oral arms. These also have stinging cells that paralyze and entangle small planktonic animals. Sticky mucus holds the prey, which is then passed up grooves in the arms and into the mouth. Unlike most jellyfish, the life cycle of the morph stinger does not involve a fixed stage. Eggs and sperm are shed into the water, where the eggs are fertilized and develop into tiny oval planular larvae covered in hair-like cilia. The planular larva changes directly into a tiny lobed saucer-shaped medusa called an ephira, which gradually develops into an adult. And over here we have, this class is Hydrozoa blue buttons. Borbita. That was an easy one. At first sight, blue buttons would be mistaken for a small jellyfish or even a piece of blue plastic. In fact, it is a hydrozoan colony that is modified for a free-floating existence. Swarms of these unusual creatures can be seen drifting on the water's surface, or can sometimes be found washed up on the shore. The animal is kept afloat by a buoyant circular disc. Around the edge hang protective stinging polyps, modified as knobbed tentacles. In the centre, underneath, hangs a large feeding polyp that acts as the mouth for the whole colony. In between this and the tentacles are circles of reproductive polyps. Unlike the Portuguese man of war, to which it is related, blue buttons do not have a powerful sting. Pretty though. This one is a deep sea jellyfish. This is a moon jellyfish. And then this is a stalked jellyfish and a stinging hydroid. More jellyfish. This is the upside down jellyfish. And this one is a box jellyfish. Mushroom leather coral. Dead man's fingers. And this is carnation coral. Oh, now that's a colourful page. Lots more corals. Jewel anemone. Look at this. This is Corynactis viridis. Jewel anemones often cover large areas of underwater cliff faces, creating a spectacular display. Individuals can be almost any colour, and they reproduce by splitting in half, making 2 new identical anemones. This results in dense patches of different coloured anemones. Each anemone has a small saucer-shaped disc circled by stubby, translucent tentacles. The tentacles have knobbed tips that worms are found in all oceans but are most common in the tropics. Let's look at this. This is a giant anemone. More coral. Look at this one, wow. This is the giant brain coral. Yeah, that looks like a huge brain. Let's read about this one. This huge coral grows as giant domes or extensive, thick crusts and can live for more than 100 years. The surface of the colony is a convoluted series of ridges and long valleys, as in other species of brain coral, and this is what gives it its name. The valleys and ridges are often differently coloured, and the ridges have a distinct groove running along the top. Typically, the valleys are green or brown, and the ridges are brown. The polyp mouths are hidden in the valleys, and the tentacles are only extended at night. In recent years, giant brain corals in the Tortugas Islands, south of the Florida Keys, have been attacked by a disease, and some have died. Particularly large colonies are popular tourist attractions in islands such as Tobago, as well as attracting divers. The coral heads attract fish, and some gobies live permanently on the coral. I presume that's one of those gobies. Flatworms. Possessing extremely thin bodies, some of which are even transparent, flatworms are among the simplest of animals. Colourful marine species mostly belong to a group called polyclad flatworms, conspicuous leaf-shaped animals, common on coral reefs, and easily mistaken for sea slugs. Some flatworms are found in fresh water, and many are parasitic. In the oceans, parasitic tapeworms and flukes are common in fish, mammals, and birds. This one here is called a candy stripe flatworm, and its Latin name is Prostherocereus. Prostherocereus pitatus. Most brightly coloured flatworms are found on tropical reefs, but the candy stripe flatworm is an exception and can be found as far north as Norway. Generally a cream colour, it is marked with reddish brown, lengthwise stripes. The head end of its flattened leaf-shaped body has a pair of distinct tentacles and groups of primitive eyes. As it crawls along, the flatworm pushes the edges of its body up into folds. It is also able to swim using sinuous movements of the body, usually found in rocky areas. It has also been seen on sand. Okay, I think we might pass over these a little bit. It's a little bit snaky and wormy. Mollusks. This is the giant clam, the largest living mollusk. Wow. Gorgeous colour. Here it is, a giant clam. Tridacna gigas. I'm probably saying this completely wrong. The largest and heaviest of all mollusks is the giant clam. Like other bivalves, it feeds by filtering small particles from the water using its ingoing or inhalant siphon, which is fringed with small tentacles. However, it differs in obtaining most of its nourishment from zooxanthellae, unicellular algae that live within its tissues, a type of relationship also associated with coral polyps. The algae have a constant and safe environment in which to live. In return, they provide the clam with essential nutrients, the carbon-based products of photosynthesis. In fact, so dependent is the giant clam on these algae, that it will die without them. The adult is sessile, immobile, and its inhalant and exhalant outgoing siphons are the only openings in its mantle, although the scalloped edges of their shell halves are mirror images of one another. Large individuals may be able to close their shells fully, so their brightly coloured mantle and siphons remain constantly exposed. Many giant clams appear iridescent due to an almost continuous covering of purple and blue spots on their mantles, while others look more green or gold, but all have a number of clear spots or windows that allow sunlight to filter into the mantle cavity. Fertilization is external, and the eggs hatch into free-swimming larvae. Before settling onto the seabed, the exhalant siphon expels water and at spawning time provides an exit point for the eggs or sperm.